So we're still trying to get information about the viscous boundary layer, and in specific, the size of this delta, which is a function of x when you have flow over a plate. So you have some flow passing over a plate or a wall, you could think of it as. It gets to the plate, there's a no-slip condition on the plate, and then that changes the flow in this region of viscous boundary layer effects. We have done an analysis using the full Navier-Stokes equations and scale analysis that shows us that this flow is going to be a balance of viscous forces and inertial forces. Pressure does not play a role. The pressure is basically uniform throughout this entire flow. So that means that these are the sizes of the forces. So we have from the x momentum equation, the inertial forces here have a scale of u infinity squared over L, and the viscous forces have a scale of nu times u infinity over delta squared. So that's going to let us just solve for the size of delta. So we can rewrite this. Delta is of order. It's going to be nu, and then we're going to have L or x over here. I'm going to put it in as x divided by u infinity, all raised to the 1/2 power. So, we can take the, this L to X transformation. L, if the plate has a finite length, we could talk about just the end of the plate, or we could apply this at any point in the plate. So if we're at this position in X, well, that's how far, we've traveled in X. So that's just going to be X there. And that's the solution. So what do we learn from this? Well, we learned that delta does increase as you go in the x direction. It increases x to the 1/2, so it's drawn approximately correctly here. That is that the viscous boundary layer does increase as a square root of x. It increases if you increase viscosity. Well, that's not surprising. We would think that the viscosity we know is what's causing the change in the flow. If the viscosity is high, those viscous effects, the fact that you're having slow-moving fluid near the plate, non-moving fluid at the plate, is going to slow down the flow more if the viscosity is high. And so that's what you see there. As you speed up the flow, the boundary layer actually gets narrower. So you have faster flow coming by, and so that compresses the boundary layer. So those are what we learned right away from the scale analysis. The form at which these different factors change the viscous boundary layer. This relationship is often written like this: delta over x is of order nu over u infinity x, all to the 1/2. And we'll explain a little bit why this is the preferred methodology. But one of the reasons is this has no units. So delta over x, delta is the thickness of the boundary layer, x is the position in the x-axis. Those would both be measured in meters. So that would have no units at all, which means that this side also has no units at all. So this is a dimensionless unit. So this has no dimensions. And we're going to see that that's very useful when we're designing experiments later. And this also has no dimensions. So these two things are the same size as each other, and they have no dimensions at all. So that's going to turn out to be a very useful grouping. And so we'll introduce it now. So the grouping on the right-hand side, that u infinity x over nu, that is the Reynolds number. So u infinity times x over nu is a very famous number in fluid mechanics. It's called the Reynolds number. And you'll see this number all the time when you're studying fluid mechanics. And so that would be, the symbol for that would be Re sub x. You can have any length scale here. It could be Re sub d or Re sub L, depending on what length scale you want to put in here. And this has, again, no dimension. So this is a dimensionless number called the Reynolds number. So the Reynolds number based on L would be REL equals u infinity L over nu. RED, if you had a tube with a diameter, would be u infinity D over nu. Those are all different forms of the Reynolds number, just depending on whether you put L or D or X, in that position. So delta over x then, the size of the boundary layer as a function of x can be written very simply as the Reynolds number based on x to the minus 1/2 power. So that is a very powerful result that we got entirely from scale analysis and applying our scale analysis techniques to the full Navier-Stokes equations. If you compare that to the exact answer, and there's a much more sophisticated mathematical technique that takes pages and pages of math, that you probably couldn't even do yet in your careers. If you want to graduate school, you may have to. But it says that delta over x is 4.92 times Reynolds number based on x to the minus 1/2. So this is the true answer. And you could say, well, it's off by a factor of 5. That's not very good. Or you could say, wow, it got everything right. It got all the scaling right. It got the effective velocity, the effective viscosity, the effective length. It got all those scales correctly. It's only off by a factor of 5. That's not even an order of magnitude. That's a great result. And that's certainly my position. If you can get a great result using scale analysis that gives you a lot of important engineering information. In certain cases, of course, exact answers are available. Here's an exact answer that is, a little bit different. But the basics of what's going on here are fully captured by our scale analysis.